Okay. Hello guys, nice to see you. So before we have finished to consider different transient processes in RC and RLC circuits based on resistor capacitor, also on like LC inductance, inductor capacitance, and resistor inductor capacitance. Also, we had a chapter dedicated to AC electric circuits. So we learned how to determine total impedance of electric circuits, which consist of different elements of AC electric circuits, in particular resistor, active resistor, capacitor, and inductor. So we figure out that there is no phase shift between voltage and current when AC current flows through active resistor. So that's why it's called active resistor, and it doesn't have any reactive component. However, at the same time, when AC voltage is applied to terminals of capacitor and inductor, they behave differently from active resistor, and there is certain phase shift between current and voltage in these devices. What is important that these phase shifts are opposite for capacitor and inductor. That's why when they connected in series, it's possible that reactive capacitive and reactive inductive resistances compensate each other since they are in opposite phases. And that particular case happens at some resonant frequency when resistance, like total impedance for the AC current of the circuit, will be determined only by the active resistor connected in series to capacitor and inductance. So this is like very general remind for the previous material which we considered. And today we proceed further, and our topic, like chapter we are going to deal with during this week is electromagnetic waves. And we have already shown that it's possible to generate electric field, like so-called induced electric field and induced electromotive force by changing magnetic field flux through certain surface, which is defined by the closed path within which this induced electromotive force is created. So that automatically means that changing in time magnetic field can produce electric field. Now we need to make one before we step in the system of Maxwell equations, which describe all classical electromagnetic interactions. We need also to show that it is possible to create a magnetic field by changing electric field like changing electric field flux. So that we haven't done yet, and that's why we definitely need to show this possibility, and then it will be already kind of closed cycle, means varying in time magnetic field can create electric field, then in the contrary, varying in time electric field can create magnetic field. So means that they can form electromagnetic wave which can spread in space. For instance, we consider for simplicity within this chapter free space without any magnetic or dielectric features of environment. So we have, let's say we deal with vacuum where we don't have some additional currents, most likely, and electric charges. However, so it really makes picture easier. And our goal for the maybe, I believe today we will just show the relationship between magnetic changing, varying in time electric field, which can generate magnetic field, and also introduce the system of 4 equations, which are called Maxwell equations, describe what they mean and what is their contribution to the modern understanding of the nature. And next lecture, we will already try to show, like derive the, in some simplified way, the speed of light, like speed of spreading electromagnetic waves in vacuum. Okay, so let me change the camera. And as I mentioned before, we need to show the relationship, first the relationship between changing magnetic field flux and induced magnetic field due to that. So in order to do that, let us consider again the known Ampere's law, which tells us that linear integral along closed path of magnetic field vector is equal to the product of mu naught, is permittivity of free, permeability of free space, magnetic permeability of free space, times electric current, which flows through the surface defined by the closed path we integrate along. This is a formulation of Ampere's law, like relationships of magnetic field and electric current. It postulates that a magnetic field can be created by electric current. However, let us consider some special case because this equation is actually valid for steady state conditions. Steady state means when current doesn't change over time, so it has some fixed stable value, and this current should be called conduction current, so that we defined very clearly. This is conduction current which flows through some conductor. And if current doesn't change, means that the electric field in the conductor is constant, so nothing is changing. However, let us consider one special case, and we will see some controversial situation. So let me share the screen. So on this figure in the left side of the slide, we see some conductor. There is some certain current flowing through this conductor, and a capacitor with some parallel plate capacitor with 2 plates and some free space between plates. There is no electrical connection, means electric current cannot flow through through this conduction current cannot flow through this capacitor. It's just a gap in electric circuit. And now for considering the Ampere's law, we can use two different surfaces, like surface S1, which is this surface bluish, and surface S2, yellowish surface, which goes through the gap between these parallel plates, but it also has the edge of this surface, of both surfaces, which defines them, it's common. So this is pass P. So under these conditions, let us now consider Ampere's law. So first we have surface S1. Surface S1, and then we need to integrate magnetic field, takes the linear integral of magnetic field along path P, closed path, which defines this surface S1, and there is some conduction current which flows through this surface defined by path P. So in this case, it will be just standard form of Ampere's law, with this integral, linear integral of magnetic field vector over this closed path will be equal to mu naught times I, which is electric current flowing through the this surface. However, let us consider another case when we have surface S2. So in this case, the path is the same, that this path also defines the surface S2. However, it goes not just through the conductor, but goes through the gap between parallel plates. In this case, there is no conduction current, because we know current cannot flow through, conduction current cannot flow through just free space or insulator. And in this case, integral of magnetic field vector along this closed path, linear integral, will give us 0, because it should be equal to mu naught times conduction current, I. And since conduction current doesn't pass through this surface S2, it's 0, and then this integral will be also equal to 0. So there is some discrepancy in this fact, which comes from the discontinuity of electric current in such circuit. And in order to address this issue, Maxwell proposed to add additional term in the right side of Ampere's law, and that additional term is called displacement current. So now let us come back to the slide where we can write. So what is this additional term? Displacement current is. So displacement current is defined as the product of epsilon naught, permittivity of free space, times the rate of changing in time the electric field flux through the surface defined by the closed path over which we take the linear integral of the magnetic field vector. So this gives us a relationship between magnetic field and changing in time electric field. To be more specific, changing in time electric field flux. So this electric field flux is equal to the integral of electric field over the area. And this area over which we take this integral, as I mentioned before, is the surface bounded by the path of integration of magnetic field vector. So what happens in this case? If, as the capacitor is, which we have seen on the previous image, is being charged or discharged, the changing electric field, so obviously we know that there is a relationship between the surface density of electric charge accumulated at the plates and electric field inside the capacitor. So electric field will be equal to sigma divided by epsilon 0. So this electric field will also change in time during charging or discharging. And this change of electric field between plates may be considered as equivalent to a current, like some conduction current, that acts as a continuation of the conduction current, and also has an impact on magnetic field, so it also can create a magnetic field. And then if we consider such additional term in the Ampere's law, we don't have this discontinuity of this discrepancy, because for surface S1, it would be electric conduction electric current, and for surface S2 would be this displacement electric current, some equivalent of conduction electric current, which passes through the surface S2. And in that case, linear integral along the same path, closed path P, will not give us different values as we discussed earlier, like mu naught times I or 0. So it will give us the same value, and this will be our next step. A little bit later, we will show that conduction current is exactly equal to the displacement current in this particular system. So now let us write this modified by Maxwell Ampere's law, taking into account this additional term called displacement current. And this modified Ampere's law is called Ampere's Maxwell law, which gives us the relationship between magnetic field, conduction, and displacement current. So integral over, like linear integral over closed path of magnetic field vector is equal to the product of mu naught to the sum of conduction current plus displacement current, or in other form will be mu naught times conduction current plus mu naught times epsilon naught times df E over dt. So this is very important concept. And now let us, as I promised, we will let us show that conduction current and displacement current in this particular case, which we consider will be equal to each other. So we know that electric field flux E. In the case of parallel plate capacitor, will be equal to E times A, where E is constant, like magnitude of the electric field vector, and it's uniform in between two parallel plates. So that's why we just take this magnitude of this electric field and multiply it by the area, which is defined according to the plates of the capacitor. So we know that when we charge capacitor, electric field is given by this equation, where sigma is this magnitude of electric field is defined by concentration, surface concentration of charge carriers accumulated at the plates of the capacitor. And this magnitude of electric field we can write in different form, which is total charge accumulated by capacitor at given instant divided by epsilon 0 divided by A, which is area of the plate. So sigma is equal to Q divided by A area. So taking this into account, we can write that electric field flux is equal to Q times A. So instead of E, we put this expression divided by epsilon naught times A. So A and A we cancel out. We get Q divided by epsilon naught. So this gives us the electric field flux between the two parallel plates of a capacitor. So now we need to, according to the definition of the displacement current, we can calculate it. Displacement current is equal to epsilon naught dF E over dt. And we know that Fe is Q divided by epsilon naught. Epsilon naught here in numerator, and there will be epsilon naught in the denominator. They cancel out. And what we have eventually, we have dQ over dt. And this is, by definition, its rate of changing electric charge with time is by definition is the conduction current. So we have shown here that displacement current is equal to conduction current. And that's why it doesn't matter which surface, S1 or S2, we will consider in the scope of the figure which we considered on the slide when I shared my screen. The result will be the same because displacement current is equal to the conduction current. So what is the main message you need to take with you from considering this Ampere Maxwell law? This law identifies the displacement current as the source of magnetic field. So it could be considered, it has different nature, but still could be considered as equivalent to conduction current in terms of creating magnetic field. So that is the first statement, which is very important. However, there is the next thing to be considered. The displacement current has its physical origin in the time varying electric field. So according to the definition of displacement current, its origin, its nature is originating from the time varying electric field between the plates of capacitor during charging or discharging process. And this automatically means and brings us the central point of this Ampere's law, Ampere's Maxwell law, is the fact that magnetic field can be produced both by conduction current, which we knew before, and also by varying in time electric field. This is very important because this is the key step towards electromagnetic waves, which can, where electric and magnetic fields are have feedback and they like each other dependent, and allow electromagnetic field to spread in free space without any additional environment, as opposite to mechanical waves, because as you remember, mechanical waves, they require some spring features of environment where these mechanical waves, like waves on the surface of water, waves on the string, sound waves, they all can be spread only in certain environments. However, as opposite to mechanical waves, electromagnetic waves, they can spread also in free space. So this is a fundamentally different type of waves, which we are going to study in more details. So now let us go to the system of four famous equations, which were set together by Maxwell, and later the validity of this system of equations and results which come which are coming out from this theory was proven by experiments carried out by Hertz. So we will discuss these aspects until the end of this lecture. So there are four equations which form this system of Maxwell equations. The first one, you kind of know already pretty much all of them because it involves different previous topics. So first of all, of the equation is the linear integral of electric sorry, it's not linear integral, will be later. It's just an integral over closed surface. So it's here, A, of electric field vector is equal to Q divided by epsilon naught. So we will discuss each equation in details afterwards. So first I will just write them down. Then second equation is equivalent symmetrical equation to the first one, but this is about magnetic field. It will be equal to 0. Then third equation is actually about it's Faraday's law, linear integral of electric field over closed path is equal to the minus change, like rate of changing of magnetic field flux. over time. And fourth equation is the Ampere's Maxwell's law, which we have just considered. Linear integral of magnetic field vector over closed path will be equal to mu naught times I times conduction current plus epsilon naught times mu naught times d f e over dt. So we have this famous system of four equations, which are called Maxwell equations. And let us talk about, discuss each of these equations step by step. So first equation is old good Gauss law for the total electric field flux. So any closed surface equals the net charge, which is enclosed inside that surface, divided by epsilon 0. So this is Gauss law. We discussed this in details some time ago. Maybe you have already forgotten, but we just remind the definition of Gauss law here for you. And this is nothing else as Gauss law, which this first equation, which gives a relationship between the electric field with the charge distribution. Depends on different charge distributions in different point of space next to this charge distribution, there will be certain electric field. And Gauss law provides a relationship between this electric field vector and electric charge distribution. So let us go to the second equation. So the second equation is the same Gauss law, but in magnetism. And it states that the net flux through a closed surface is equal, like net flux of magnetic field vector of a closed surface is equal to 0. So what does it mean? That actually we discussed also earlier when we introduced the magnetic field in during our course. That means that magnetic field lines do not begin or end at any point in space as opposite to electric field, because we know that electric field lines begin at positive charges and end at negative charges. If magnetic field lines do not begin and end at any point in space, means that this equivalence of electric charges, so-called, let's say, magnetic charges, do not exist. So these magnetic charges would be, they should be called magnetic monopoles, and it have not been observed. These magnetic monopoles haven't been observed in nature. So that is the statement of second equation, which is Gauss law in magnetism. So nothing really new. The third equation is old good Faraday's equation. So we spent also quite a bit of time working with this equation, and this equation gives us the relationship between induced electric field and changing magnetic field. So it shows that varying in time magnetic field can create electric field. So being more precise from a mathematical point of view, the linear integral of electric field vector along closed path is equal to the minus of the rate of changing magnetic field magnetic field flux over time. So this is the third and the fourth Maxwell equation. This is Ampere Maxwell Law, which gives us the relationship between magnetic field, conduction, and displacement current. Very important. If third law tells us that electric field, like first and third equation in this system of equations, of Maxwell equations, tells us that electric field can be created either by electric charges or by changing magnetic field. The fourth Maxwell equation tells us that magnetic field in its turn can be created by conduction current and displacement current. And this displacement current has the nature, the origin of varying in time electric field. So means that electric current and varying in time electric field can generate magnetic field. So all this system of equations, they are related to each other and support each other in terms of describing electromagnetic interactions. There is one more equation which is necessary in order to fully describe all classical electromagnetic interactions, and that is called Lorenz Force Law. So if electric field vector and magnetic field vector are known in certain point of space, and then we locate with some velocity vector electric charge Q, this U electric charge, and this electric charge moves with some velocity vector V. In the moment when this charge is located in this given point of space, total electromagnetic force, in this case, acting on this charge will be equal to Q times E vector plus Q times vector product V multiplied velocity vector multiplied by magnetic field vector. So this equation is called Lorenz Force Law, and together with the system of four Maxwell equations, they describe all possible classical electromagnetic interactions. So one of the main outcome of the Maxwell system of equations is that, for instance, that what we are going to do next lecture, when combining third and fourth Maxwell equations, it is possible to derive the speed at which electromagnetic waves will spread in free space. And the value which was obtained is actually the speed of light, c, which was experimentally measured and was already known with certain accuracy. So that automatically proves that light, the visible spectrum, in the visible spectrum, which we can see, so we call this light, has electromagnetic nature. So it was definitely not clear, and also during so this comes from the theory, and it's really a great achievement of theoretical physics in predicting the nature of phenomena which we observe but don't understand. And such a great scientist as Hertz, an experimentalist, carried out a number of brilliant experiments showing, first of all, generation and detection of electromagnetic waves. And afterwards, he showed that these electromagnetic waves behave similarly as light. So we will study this in the part of our course about light, but this light and as electromagnetic waves and any other electromagnetic waves with different frequencies can be reflected and also some interference effects can be observed. So he definitely has shown that light and electromagnetic waves have the same nature, and technically light is an electromagnetic wave of a certain frequency range. So let us come back to the slide which I shared previously, and I will show you a schematic of Hertz experiment, which is shown in the right side of the slide. So the idea is to use an induction coil, which, for instance, you run some steady state current, then you turn off the current because of self-induction. This coil generates induced electromotive force. This induced electromotive force is applied to some spherical electrodes placed on some distance, and such a system works as LC circuit. So there is some inductance L and capacitance C between these spherical electrodes. This large induced electromotive force creates a very strong electric field between these two spheres and results in acceleration of electrons in air. So there's always some small amount of ionized molecules of oxygen or nitrogen. So there are some ions and some electrons. They are accelerated by this strong electric field, start to bombard neutral atoms which form the atmosphere, ionize them, create new ions and electrons, and over time, the resistance of this air between two spheres changes quite rapidly because of these spontaneous ionization events in the space between these two spheres. So that results in very high generation of very high frequency electromagnetic waves, because these different portions of electrons are accelerated and then slowed down by collisions with atoms, and again they create new electrons, again accelerated. That creates a generation of high frequency electromagnetic waves, and they spread in space from this LC circuit. So in order to proves that something is spreading, that something is created, you definitely need to measure this. So oops. I don't know what happened. Hope you hear me. So it was just some glitch with. Okay, cool that you hear me. I don't know. Zoom just stopped working and reconnected. So let me share again this screen, and I finish this explanation of the Hertz experiment. So by changing the distance between these two spherical electrodes and changing the inductance of the receiver, when LC parameters, inductance and capacitance of this receiving circuit was matched with the generating circuit, he could see some discharges between these two spherical electrodes. And that was a clear evidence of detecting electromagnetic waves, because they were not connected, so they were electrically decoupled from each other, the generator of electromagnetic waves and receiver of electromagnetic waves. And the only possible source for creating electric discharges in the receiving LC circuit was absorb this like, generated electromagnetic waves, which results. So this was this experiment results in the experimental provement of existence of electromagnetic waves, defines the possibilities of generating and detecting them. So that is one of the key achievements of Hertz in terms of experimentally supporting Maxwell's equations, and together with theory and experiment develop this field of research focused on electromagnetic waves, which is really broad and sophisticated currently. So with this, I believe this is everything what I wanted to share with you during this lecture. I change me again. So next lecture we will focus on the derivation of speed of spreading electromagnetic waves in free space, which is based on combination of the third and fourth Maxwell's equations. This will be done in a bit more like simplified way, since the direct solution of the second order differential equation comes beyond the scope of our course, but we will step by step try to show how this speed of light constant c can be derived based on electromagnetic theory described by the system of Maxwell equations. Thank you very much for your attention. If you have any questions, you're welcome. If not, then
Thank you for this lesson. I have a question, one question about our next midterm. It will be on like 10th April, I guess. Yes. And what kind of like topics it will consist? Like from 13 chapter or from 14 chapter?
One second. Yeah, I just got a message for the preparation for this midterm. It will be chapter 13, 14, 15, 16.
Okay.
From 13 to 16.
Yes, thank you.
You're welcome.
Goodbye.
Okay, guys, thank you for attention. Have a good evening. Take care and see you on Wednesday. Bye-bye.